So, what other current limitations do you see exist in the renewable energy space outside of costs and specifically to the points that are materials related?
That's a good question. Actually, I'm quite inspired by the journey, the trajectory that PV, the photovoltaic cells, went through. As an example of how a renewable energy industry can develop. Because when I was young, it was expensive. You need silicon wafers. They cost a lot of energy to produce. That makes it again expensive. Footprint very far away from ideal. So will you ever get a return on your investment, both money-wise, but also carbon footprint-wise? And when you look at the reduction of raw material use that has been achieved in that industry, and the extremely low cost of renewable electricity right now, that is unbelievable what has been done there, again, by many scientists, also a lot of material scientists. And of course, engineering as well. I want to mention also here, again, the role of engineering and manufacturing, because nowadays it is like roll-to-roll printing of PV. It has become a massive industry. Extremely cheap. They come in different shapes and sizes to make sure you can apply them in many different areas. So it is very cheap, it is mass produced, and I think that is a journey that many other renewable energy areas will need to go through. We just discussed the hydrogen economy. Same thing. It is this learning curve that we will all need to go through. And every time we learn from, maybe in PV, it took 20 years or 30 years, whatever the number. Can we do it in 15 or in 10 this time? Because you learn from what such an industry went through, a related industry went through. But it gives me a lot of energy because we can apparently do more with less. And that journey can be extremely successful, whether it was with computers, computer power, or the PV industry. I'm sure we can also copy that in the hydrogen space, for example.
So moving towards the technology side of this a little bit. So at JM, you use several platinum group metals in your catalysts and in fuel cells and electronics. But there are some technical challenges with being able to recycle these rare metals. And of course, they're extremely valuable, so recycling them is of the utmost importance. So talk to some of the challenges that the industry is currently facing in recycling platinum group metals, or Pgms for short. For our listeners, platinum group metals are typically defined as the metals which include platinum, ruthenium, rhodium, palladium, and iridium, broadly speaking. And how can some of these challenges be overcome to better enable the sustainable utilization of these materials in the future?
Yeah, I think that is a very good question. But also we have a long history in trying to answer those questions. So
Right.
Let me start with the history of Johnson Matthey. It's a company, it's more than 200 years old. And at the heart of the origin, the roots of the company, it's all about refining and purifying platinum group metals. So we have a 200-year history in this space. We have extremely sophisticated processes, and we still innovate a lot in that space. We produce these metals with 99.95% purity. And in the course of these 200 years, we have improved these recycling processes so much that actually the recycling of platinum group metals is not a big issue. It is very easy to take the catalytic converter from a car from 20 years ago, and after it ends of life, the customers bring it back and we recycle. We take out the noble metals and we use them again. That is common practice, and we're very good at it. But that has, of course, a long history. What is very important in this context, if you know that a material is relatively rare, take into the consideration immediately when you start to develop a certain use for such a material, what am I going to do with it at the end of its active life, industrial life? So I call that design for recycling. And at Johnson Matthey, we are very fond of this circular economy. We think that it is a business imperative. It is really important, and it's a demand from our customers and supply chains to show that we can think and act in a circular way. So our scientists, when they have ideas about a new application, a new catalyst, whatever, for these noble metals, but also for other materials, before they start, they think things through. What are the potential different avenues we can follow? What are the potential different solutions we can find? What would be the sustainability profile of each of those solutions, carbon footprint, but also end of life part, taking it into account, and then choose the solution that has the best overall life cycle assessment, the best picture for also using them at the end of the life of the catalyst. How can we take it back and recycle it or reuse it easily? So these design for recycling principles we take into account from day one before we start the R&D project for all our projects, because we know how important it is. We're very well skilled at it. And we also try to think, how can we proliferate and use our knowledge that we have acquired for PGM recycling, the platinum group metals, also for other raw materials. It's really in our DNA at Johnson Matthey to think circular from the onset.
No, that's fantastic, especially these materials, which are just so incredibly intensive to be able to extract. So to stay on the topic of platinum group metals, you mentioned earlier in our conversation that there had been developments in using PGMs in cancer therapies. So I was curious if you could dig into that a little bit more and describe what some of these novel cancer therapies, which involve these platinum group metals, what those entail and what makes them so promising.
This class of materials, it was found, I think in the 60s, it was invented that these certain platinum compounds, cisplatinum in particular, that they had an activity against fighting cancer cells. And the side effects were very severe. And very early after these first inventions, Johnson Matthey tried to help the pharmaceutical industry develop new types of platinum compounds that were as active, but with somewhat more limited side effects. So nowadays we know a lot more about how the different cancer types need to be treated. And the platinum group is quite a harsh type of medicine. So they are used for very hard to treat aggressive cancer types. But there's many other drugs that have been developed that are a little bit less damaging to the body and have less side effects for other types of cancer. But we were involved very early and helped with the chemistry because we knew so much about the complex chemistry of platinum in particular at the time. And so we tried to help the medics. And we also helped produce the raw materials for those drugs. And we still do.
And so one little personal anecdote there, actually. When we were preparing for this episode, we actually watched a video about platinum group metals. It was by a channel called Periodic Videos, but there was a chemist in a JM facility. For our listeners who want context for what these metals look like and how ridiculously expensive they are, he was essentially playing with iridium and platinum and some of these other materials in a very controlled environment. But I really thought that was a fantastic way of understanding the significance of these materials that your industry and your company in particular works with.
I think it's a great group of metals. As a metal, they're very versatile and they help in the car, for example, to purify the exhaust gas. If you start to do chemistries with them, you can use them as, for example, an anti-cancer drug. And I think, it shows the versatility of these relatively rare, expensive materials, but also the incredible benefits they can offer.